In this lecture set, we will be talking about optimization, particularly the unconstrained type. Recall in our previous lecture on linear programming, we have an objective function which you will maximize or minimize subject to some constraints. Here, the difference is that there are no such constraints. And second, the objective function may be nonlinear. Okay, so it's not necessarily linear. So in this particular case, we will be tackling the single variable case where the function only admits one variable, call it x. So let us define some terms first. Suppose we have a function f, which is a function of one variable. Okay, so it's like f of x, where there's only one variable inside here, x, within the domain D. Okay? So an element x star in the domain is a global maximizer of the function f if and only if this thing happens. Okay? So when you plug in x star to f, you will have a value, f of x star. Okay? So for all other elements x, for all other x's in the domain D, when you plug in any other x in the function, this will never be higher than when you plug in that particular x star. Okay, so try another x. If you plug in that x into the function, it will yield a value that's no higher. So this is less than or equal, no higher than the value of the function at x star. Then we call x star a global maximizer. Okay, so once you plug in x star to the function f, this value, f of x star, is called the global maximum of the function f. Okay? And x star is called the strict global maximizer is when you find x, other values of x in the domain, you plug in x in the function. Okay? If you do that, it will yield values f of x that will be strictly lower than when you plug in x star in the function f. Okay, so once you plug in x star in the function f, this will yield the value fx star. Get any other value x in the domain, plug it in, and for any other x, once you plug it in, it will always yield a strictly lower value than f of x star. Then we call x star a strict global maximizer of the function f. Okay, and the value f of x star is the strict global maximum. Great. So analogously, we have the global minimizer whenever you find an element x star in the domain D, and when you plug in x star in f, okay, it will constantly yield a value that's always lower, okay, or equal to all other elements, all other x's in the domain D. Okay, so think of any other x in the domain, plug it in the function. Okay, that will yield a value that's not lower than when you plug in x star in f. Okay, so when that happens, that when you plug in x, it will yield a value that's not lower than when you plug in x star. We call x star a global minimizer. Okay, and this value f of x star, once you plug in the global minimizer x star, is called the global minimum. Okay, so the global minimum is a value. The global minimizer is an element x star in the domain. Okay, and then analogously, we could call x star a strict global minimizer. Whenever you plug in x star in the function, it will yield values that is strictly lower than any other x in the domain. So if you plug in any other x, plug it in the function f, it will always yield a value that's strictly higher than when you plug in x star in the function. So if that's the case, then x star is called the strict global minimizer. And the value of the function f of x star when you plug in x star is called the strict global minimum. Now let's go to define what a local maximizer, local minimizer, local maximum, and local minimum is. Okay, so the only difference from the global definition, global maximizer, global maximum, global minimizer, global minimum, is that we restrict the domain uh, to an open interval AB. Okay, so instead of the whole domain, let's uh, let's restrict it to an open interval AB, which is in the domain. Okay, so if you find an element x star that yields a value not lower than any other x in this open interval in the domain, not the whole domain, but just a particular slice of that domain, then we call x star a local maximizer. So as the name implies, it's just local to that open interval, not to the whole domain. Okay. For all x in the domain D that are also in this open interval AB. Okay, so the difference between the global and the local is that the local you're just focusing on a subset of the domain, particularly the interval AB, the open interval AB. Okay, so that value when you plug in x star, okay, is called the local maximum of f. Okay, so whenever x star, which is in the domain that are contained in the interval AB, if you plug in that x star to the function f, and it always yields a higher value than any other x inside that slice of the domain, okay, then you call x star a strict local maximizer. And the value f of x star the strict local maximum. Okay. Analogously, x star is a local minimizer in the slice of the domain AB. Okay. Uh, Whenever you plug in x star to the function and it yields a value not higher than when you plug in any other x also in that slice of the domain. Okay. So you call that element x star a local minimizer because it's only local to that part of the domain. Okay. And when you plug in x star to f, it's called the local minimum of the function f. And finally, if you plug in x star and it gives you strictly lower value than any other x, once you plug in any other x in the function, x star gives you a strictly lower value in that slice of the domain, then x star is called the strict local minimizer, and the value f of x star is called the strict local minimum. So in terms of nomenclature, so a maximizer or minimizer is also called an optimizer or an extreme point. Okay, so it's a point in the domain. A maximum or a minimum is called an optimum. Okay, so it can be called an optimum or an extremum. Okay, so these are values of the function. And whenever appropriate, we modify that optimum or optimizer global or local. So here's an example to clarify the concepts. We have the entire domain as the interval AF. Okay, so this is the entire domain. Okay, A to F. This whole area here is the entire domain. Okay, great. Now, local maximizers are points A, C, and E. Okay, So A is a local maximizer, C is also a local maximizer, and E is a local maximizer. Why? Because if you create an open interval, say this is interval, uh, let's call it U1, V1, okay? So these are numbers, okay? So in that interval, in that slice of the domain, point A will give you the highest value of the function, okay? So C is also a local maximizer because whenever you restrict the domain to say U2 V2, okay? So this is your restriction of the domain, this area over here, okay? That's your restriction of the domain. Okay? That's your open interval. Now, if you restrict that domain to this interval over here, you see that at point C, this will yield the highest value of the function. Okay? So it's a local maximizer. Same here with E. If you just consider this slice of the interval, this slice here corresponding to say U3, V3, so these are numbers, okay? This open interval here. Note that within this open interval, you have E garnering the highest value of the function. So the AC and E are local maximizers. Okay. So in the same manner, points B, D, F are local minimizers. Why? So if you restrict the domain to be here, okay, this part, B will give you the lowest value of the function, point B. D, on the other hand, if you restrict, say, the domain to be in this part, in this open interval, okay, then D in this interval will give you the lowest value of the function. And F, if you restrict it to this open interval, okay, F will give you the lowest value of the function. Great. So that's local maximizers or minimizers. The important thing to note is that it gives you the highest value of the function within the restricted part of the domain. Okay, an open interval here. Now, what are the global maximizers and minimizers of this function? Okay, so global, by its term, uh, by the name itself, is that we have to consider the whole domain. Okay, so what is the whole domain? The whole domain is from A to F, this part, okay? So that's the whole domain of this function. Now, the question is, which points in this whole domain gives you the highest value of the function? Well, it is point C because at point C, the highest value is attained, okay? The highest value of the function is attained. On the other hand, where is the lowest value attained in this whole domain? Here, it's clearly point F because any other value in this domain will be higher, strictly higher than at point F. Okay, so it's a global minimizer and it is a strict global minimizer because point F, if you take any other point, it will yield a higher value than of the function than at point F. Okay? So this is how to illustrate the concepts of local and global maximizers or minimizers. Now, how do we identify where such optimizers are located? Okay, so here we'll discuss the first derivative test. So suppose we have a function f that's differentiable on the interval AB. So in the interval AB, okay, in this slice of the domain, okay, the function f is differentiable, meaning you can take the derivative of f. Okay, and suppose that we pick a point in AB, call it x. Okay, we pick a point in AB and x, and this happens first for x which are between the point A and x star. So we have x star here. Okay, we have x star for, so for any other for any x between A and x star. Okay, this is what the symbol means. So x could be here, for example, call it x1. Another point would be here, call it x2. So this is between A and x star. So when this happens, f prime x is greater than 0, which means that the slope of the function, the tangent line at that point, is positive. So at that point, x1, for example, this tangent line, f prime of x1, is clearly upward sloping, so it's positive. Okay, and at another point between A and x star, call it x2. Okay, so in x2, let's do the same exercise. At that point, construct the tangent line of the function. This is f prime at evaluated at x2. Clearly this is also upward sloping, so it's positive. So whenever that happens, so whenever all the x between A and x star will give you a positive tangent line, positively sloping tangent line, or the function, alternatively, you see that the function is increasing. Okay, the function is increasing to the left of x star. And then whenever you choose another point x between x star and b, okay, so let's call this x3 and x4. Okay, so these are uh, points, these are x's between x star and b, point b. So whenever that happens, and then you evaluate the derivative at that point, so in this case, f prime of x3 is less than 0. Clearly, it's downward sloping over here. And in the same manner, uh, at x4, you could clearly see that the tangent line is also downward sloping. So f prime at x4 is also less than 0. So whenever you have uh, the slope of the tangent line downward sloping to the right of x star, and the slope of the tangent line upward sloping to the left of x star, okay, so to the left of x star, all tangent lines are upward sloping, or the function is increasing, and to the right of x star, all tangent lines are downward sloping, or the function is decreasing, then we say that x star is a local maximizer of the function f. And the value here, this one, call it f of x star, okay, that value, this is called the local maximum. Okay, so this is the local maximum, this is the local maximizer, and this thing happens where any point to the left of x star will yield you a positive tangent line, positively sloping tangent line, and the points to the right of x star will give you a negatively sloped tangent line. Then x star is a local maximizer, and the value f of x star is a local maximum. On the other hand, um, if we have points between a and x star, call this, say, suppose this is x1, this is x2. Okay. So in contrast to the example earlier, points between a and x star, or to the left of x star, will yield you a negatively sloped tangent line, okay, or the function f is decreasing to the left of x star, okay, between a and x star, and for points to the right of x star, call this x3 and x4, okay, the tangent line at those points are upward sloping, or the function is increasing, then we call x star the local minimizer, okay, and this value of the function at x star, call it f of x star, okay, this is a local minimum, okay, local because you're restricting the domain to a and b, okay, in this slice of the domain. So in contrast with the example earlier, points to the left of x star will yield a negatively sloped tangent line, and points to the right of x star will yield you a positively sloped tangent line. Then x star is a local minimizer, and the value at x star, f of x star, is a local minimum. So now let's go to an example. Okay, so suppose we have this function f of x is equal to x cubed minus 3x minus 4. Now we get the derivative of this function with respect to x. So we have 3x squared minus 3. Okay, when you isolate 3 and you solve for x squared minus 1, then you come up with the expression 3 times x plus 1 times x minus 1. Okay, so clearly you see that the signs of this term x plus 1 and this term x minus 1 will govern the sign of f prime x. So if one of them is negative and the other is negative, it will be positive. If one is negative, then the other positive, then you have a negative slope of the tangent line. And if they're both positive, then f prime x is positive, and so on and so forth. Okay, good. So first, let's identify the stationary points. You get that by setting this derivative equal to 0, and this will be equal to 0 whenever x is either negative 1. So when x is negative 1, then this term will be equal to 0, and therefore the whole equation will be equal to 0. And another point when x is equal to 1, so if x equals to 1, this term will be 0, and so therefore the whole term will be 0. So the stationary points are two values of x's, x star equals to negative 1, and the other one is, we call it x star star is equal to 1. Okay, so just reiterating what I said, the derivative, the slope of the tangent line, is wholly determined by this two expressions over here. What we'll do next is we'll just tabulate the signs, tabulate the sign of the derivative f prime x based on the interval given by the stationary point. So we have three such intervals. Okay, the first interval is when x is less than negative 1. The second interval is when x is between negative 1 and 1. Okay, and the third interval is when x is larger than 1. Okay, so when x is less than negative 1, okay, so in this expression, so there are two expressions that will govern the sign of f prime of x, x plus 1 and x minus 1. These are this expression. So whenever x is less than negative 1, so for example, negative 1.5, so negative 1.5 plus 1 is negative 0.5, so it's still a negative number. Okay, so the sign of x plus 1 whenever x is less than negative 1 is negative, and the sign of x minus 1 when x is less than negative 1 is negative. Okay, so negative minus negative 1 is negative. So therefore, if x plus 1 is negative and x minus 1 is negative, then the sign of f prime x will be positive. Good. Now let's consider the second interval. So between negative 1 and 1, this sign. So if it's x is between negative and 1 and 1, the sign will be positive. So for example, you have negative zero point 0.5. Negative zero point 0.5 plus 1 is positive zero point 0.5. So therefore, this is positive. And here, when we have x between negative 1 and 1, okay, so uh, for example, let's take 0.99. So 0.99 minus 1 is still negative 0.01, so it's still negative. Okay, so therefore, when x plus 1 is positive and x minus 1 is negative, so the sign of f prime x in this point, in this interval, is negative. Good. And finally, if x is greater than 1, so if x is greater than 1, clearly this is positive. If x is greater than 1, say 1.5 minus 1, it's still positive. Okay, 1.5 minus 1 is positive 0.5, it's still positive. So therefore, the sign of f prime x, if both of these terms are, both of these expressions are positive, then we'll end up with a positive sign. Okay, so let's just draw this value for x. Okay, so we have this interval, we have less than negative 1, between negative 1 and positive 1. So greater than positive 1. Okay, so we have this interval. So if you have values for negative 1, the sign of f prime x is positive. So to the left of negative 1, f prime x is positive, so it's upward sloping. The function is upward sloping. Okay, so between negative 1 and 1, the sign of the derivative is negative, so it's downward sloping. Okay, and then finally, for values greater than 1, it's positive, so it's upward sloping again. So clearly, when you have this pattern, we have negative 1 is a local maximizer, because to the left of negative 1, the function is increasing, and to the right of negative 1, the function is decreasing. Okay, so at 1, in contrast, at 1, this is a local minimizer, because to the left of 1, the function is decreasing, and to the right of 1, it is increasing. Okay, so here, just by examining the signs of the derivative, we can see whether a stationary point is a local maximizer or local minimizer. So in fact, if you look at the graph of the function that we had earlier, x cubed minus 3x minus 4, it looks like this. So clearly you can see that at x equals to negative 1, this is a local maximizer. At x equals to 1, this is a local minimizer. Okay, so like I said before, to the left of negative 1, you have an increasing function. The value of the function is increasing, and to the right of negative 1, it is decreasing. So therefore, this is a local, this point negative 1 is a local maximizer, and this point is a local maximum. This value is a local maximum. On the other hand, at x equals to 1, for values to the left of 1, the function is decreasing, and for any value of x bigger than 1, the function is increasing. So therefore, 1 over here is a local minimizer, and the value here is called the local minimum. So that's the first derivative test. So let's have another example. Okay, so suppose we have this function over here where for values x less than or equal to 1, you have x, and for values x greater or equal to 1, then you have negative x plus 2. So the graph of this function is this, kind of like a triangular shape. So notice that there is a kink here. So whenever you have a kink, the derivative at that point is undefined. Okay, so at that particular point, x star equals to 1, this derivative f prime x is undefined. Okay, undefined. However, we can still use the first derivative test, because to the left of 1, okay, for values of x to the left of 1, we can see that the slope is increasing. Okay, the slope is increasing. Uh, and for values bigger than 1, the slope is decreasing. Okay, so the function here is increasing to the left of 1, and the function is decreasing to the right of 1. So therefore, at that point x star equals to 1, the value of the function is at its highest. So x star equals to 1 is a global maximizer, okay, because we're defining it over the whole domain. So the whole domain is essentially from negative infinity to positive infinity. Okay, so you can stretch this line all the way to negative or positive infinity. It's still true that at this point x star equals to 1, it will yield the highest value. So therefore x star equals to 1 is the global maximizer, and f of x star here is the global maximum. Okay, so even the point is that even if uh, the derivative at this x star equals to 1 is identified, we can still use the first derivative test to determine the presence of maximizers or minimizers. So similar to the example earlier, let's have this function. Uh, it's the cube root of x squared. Okay, so you take the cube root of x and then you square it. Okay, and so this derivative, if you take the derivative of this one, notice that x is here in the denominator. So whenever x equals to 0, this derivative is undefined. Okay, so in fact, if you have this function, this is the graph of the function. Okay, at x equals to 0, this derivative is undefined. But still, we can use the first derivative test. So at points less than uh, 0, at any x less than 0, you see that the tangent lines are downward sloping, or equivalently that the function is decreasing, and to the right of x star the function is increasing, or the slopes of the tangent lines are positive. Then we say that x star here is a global minimizer of f. Okay. So it's not explicit here, but let's just make it explicit. X is an element of the real number line. Okay, so this can extend there and there. Okay, so here the value of the function is at its lowest, so therefore x star will give you is the global minimizer because it will give you the lowest value of the function f of x star. So f of x star here is a global minimum. In fact, it's a strict global minimum if you want to be technical. Okay, so even if the lesson is even if the derivative doesn't exist, it's not defined at certain points, you can still use the first derivative test, meaning look at the slopes of the tangent line to the left and to the right of a particular point. Okay, let's define what critical points are. So a point x star, okay, is called the critical point of the function f if and only if these two things happen. When you plug in x star to the derivative of f which is f prime, okay, when you plug in x star to f prime, it will equal to 0. Okay, so that's one. It's a critical point if this is satisfied, or whenever the derivative at that point x star is undefined. So in the previous two slides, we saw such a case. So whenever this case or this case happens, then x star is called a critical point. Okay. So another name for a critical point, if it satisfies the first condition, or whenever the derivative is equal to 0 at point x star, this critical point is also called the stationary point. Okay? So whenever f prime x star equals to 0, x star is also called the stationary point. So whenever you have stationary points, those are candidates for being optimizers. Okay. So for example, you have this graph. Here we have x star being a local maximizer, because at x star this function f of x, which is this yellow line, the graph of which is this yellow line, x star uh, gives you the highest value of f of x. Okay, so if you notice at that point x star, when you draw the tangent line, okay, the tangent line is horizontal. Okay, so this is true for any uh, function that is differentiable if x star is a maximizer or minimizer, a critical point, then you have the tangent line at that point uh, to be horizontal. Okay? So what is a horizontal tangent line? Okay, a horizontal tangent line means the slope is equal to zero. There's no rise for the run. Okay, so the rise is zero, so it's flat. Okay, so this is just equivalent to saying that the slope of the tangent line f prime at x star is equal to zero. Okay, so it's flat at x star. So once you plug in x star to f prime x, it's equal to zero. This is the same thing as saying that the tangent line is horizontal at that point. In the same manner, suppose we have this function f of x. Now at x star, this value of the function will be at its lowest, so therefore x star is a local minimizer. Okay, so here the slope at that point x star is also horizontal. The slope of the tangent line is also horizontal. So in the earlier case, when we had this function, okay, where x star is a maximizer, the slope there is horizontal. The same case when it's a minimizer, the slope here is also horizontal. Okay, so pardon me, this should be minimum. Okay, but you see the point, right? So whether it's a maximizer or minimizer, at that point at the x stars there, the slope of the tangent line are both horizontal. Okay, so in those cases, f prime of x star is equal to zero. So this discussion now brings us to the first order necessary condition for optimality. Okay, so it's embodied in this theorem. So suppose your function f is differentiable. Okay, is differentiable on an interval AB. Okay, so this slice of the domain, and that open interval AB contains a point x star, and that x star is either a local maximizer or a local minimizer, as in the case of the two examples just before this slide. Okay, if that happens, then x star is a stationary point of f. Okay, which means that by the definition of the stationary point, the slope of the tangent line at such x star is equal to zero, or the slope of the tangent line is horizontal. Okay, so again, if f is differentiable and x star is either a local minimizer or maximizer, then the slope of the tangent line at that point x star is horizontal or equal to zero. So just a few caveats of the theorem that we had earlier. So the theorem, one essential point of the theorem is that the function f should be differentiable at the candidate optimizer x star. Okay. Um Here, in this case, where we saw this in an example earlier, we had we had x star equals to zero to be a global minimizer. Okay. However, the derivative f prime of x evaluated at this point is undefined because the derivative is this one. So therefore, we can find optimizers that are not necessarily stationary points. Okay, so stationary points meaning that f prime at x star equals to 0 is satisfied. Okay, so this is a critical point but not a stationary point. Okay, so optimizers can be non-stationary points. Okay, can be a point which is not a stationary point. Also, the theorem, an essential ingredient there is that the candidate optimizer x star should be an interior point. So it's interior, it's inside the open interval AB. Okay. So, however, in this case, so look at the function f of x. Okay. So um, at point x star, which is an endpoint of the interval x star b, okay, the function f of x attains its highest value. Okay. But at that point, the tangent line is not equal to 0. It's just an endpoint. Okay. So an optimizer x star can also be an endpoint. It doesn't necessarily need to be a stationary point where f prime x star is equal to 0. In this case, the slope of the tangent line at x star is definitely not horizontal. Okay. But it's still an optimizer. So there can be optimizers that are not stationary points. And another caveat of the theorem that we had earlier is that the theorem doesn't say that if x star is a stationary point, meaning that x star satisfies this, if x star is a stationary point, it doesn't necessarily mean that it is an optimizer. Okay? So the converse is not true. Okay? So if you find stationary points, it's not automatic that they are optimizers. So for example, you have this function f of x equals to x cubed. Okay? So this is this purple line over here. The graph of this function is this purple line over here. If we take the derivative of x cubed, we have 3x squared. Okay? And for this to be equal to 0, x star equals to 0 will satisfy this condition, f prime 0 equals to 0. Okay? So x star equals to 0 is a stationary point because it satisfies f prime x equals to 0. Great. So if we plug in 0 here, 0 squared times 3 is equal to 0. Great. So x star equals to 0 is a stationary point. But the question is it an optimizer? Is it a maximizer or a minimizer? Okay. Not necessarily, because as you can see here at x equals to 0, this is neither a minimizer nor a maximizer. Okay, so it will not give you the highest or lowest value of the function. In fact, this is what's called an inflection point. Okay, inflection point. So you see here that this is a stationary point, but it doesn't give you the highest or lowest value of the function. And such stationary points can also be inflection points. So the point of the theorem is, if it's a stationary point, it doesn't automatically mean that it's a maximizer or a minimizer. Okay, the theorem doesn't say that.